Today is just like any other day. I wake up at 7:45 a.m. as usual to get ready for my 8 a.m. lectures at my favorite Zoom university. I open my schedule and try to download the lecture slides to help me follow the lecture. I guess not. I come early to see my favorite lecturers.
Good morning, students.
But fatigue quickly set in. I thought to myself, I can't believe this lecture is 1.5 hours long. I decided to take matters into my own hands. I need someone to take notes for me, but my friends won't share their notes with me if I skip this lecture, so I got to depend on myself. I opened PyCharm to run my Python script. The script automatically takes screenshots for me, so that I don't have to bother using the stupid snip tool. Mission accomplished. Another win for me at Zoom University. Time to rest to fight another day. If you're a student during the COVID-19 pandemic, you will definitely understand what it's like to have all of your lessons on Zoom. You may miss the real-life interaction with your friends, talking during lectures and disturbing other people. But on the other hand, Zoom lectures give you the power to take notes so much more easily. One example is by screenshotting every single slide that the lecturer shows to you. Well, you may be asking, why screenshot when the lecturers will give you the PowerPoint slides anyways? Some lecturers do promise to give you the slides after the lecture, but most of the times they forget, and you never receive the notes, or the notes get uploaded so late that you're already busy surviving another wave of lectures that you forget about downloading the previous slides. So my schoolmates and I have been screenshotting every single slide, even if the lecturer promises to give you the slides after that. It seems good and all to be able to save every single slide that the lecturer shows us, but unless you have a very powerful brain, it's difficult to process and understand each new content of the slide immediately while doing a set of functions on your computer to screenshot and paste the screenshot into your notes. In other words, it's difficult to understand new content while you're multitasking to save the slides. One day, I decided I had enough of trying to drag the snipping tool for every single slide. And due to my obsessive but not compulsive disorder, I was getting annoyed that sometimes my screenshots would miss out certain info, meaning that I have to screenshot again, or my screenshots would be too big, and thus all the important info in the screenshot will look too small. Now, if you have in real life lectures, then this video is not for you. But if you'd like to find out how this script works and how painstakingly painful the trial and error process was to make this script, then stay on to find out. Here's how my script works in a real Zoom meeting. I had to use my phone to record the script in action because I didn't want to record the person's face.
Can you please?
Here's another example.
Well, for anesthetic factors, usually these are the few factors. Okay, so for every op, right, if you talk about these 4 factors, you're unlikely to miss anything important. Okay, analgesia, temperature management, fluid management, as well as DBT prophylaxis, right? Okay, so let's go on to, he will be undergoing general anesthesia with endotracheal injury.
So let's say I'm in a lecture right now and I'm too lazy to take down the screenshots. What I'm gonna do is I'm just gonna press the play button here, run the script, and what's gonna do, doesn't look good. What I'm gonna do is I'm actually going back to the script and I'm gonna set the right settings for this case. So this screenshot size is the size of the screenshot I'm gonna use, but we're not gonna change that first. I'm gonna change the offset of the start of the screenshot. So start screenshot will be on the top left. We're gonna change this to maybe about let's see, this x-axis, so we're gonna make it more to the right. So we're gonna add about 300 here. And then for the y-axis, we're gonna keep it the same because it seems to be okay. And then what we're gonna do is we're gonna increase up the y size of this screenshot. So I'm gonna do the same thing. Oh, it's too much. I'm gonna actually maybe decrease it. Okay. The screenshot area is a bit too long along the horizontal axis. I need to cut it down. Okay, perfect. So once I've set the right settings that is specific to each lecture, all I need to do is just leave the script be, and every time it changes the slides, the script will paste a screenshot into the notes. Okay, there's a bit of lag when changing the slides, but usually in a real lecture, the slides will change almost instantly. So how this script works is that whenever the script takes a screenshot, it will compare the pixels of this screenshot with the previous screenshot and calculate the percentage difference in the color of the pixels. Once the percentage difference hits a threshold, the script will proceed to paste it in my notes, which in this case is Microsoft Word. Now I must assert that this script is very flexible. It works with any other online lecture platform like Microsoft Teams. It also works with any other note-taking app like OneNote. This script wasn't really easy to create because I had difficulty deciding how to compare the percentage difference between images. Because apparently there's many different ways to do it, and some of them are just horrible ways to do it. Now before I explain my script, I'd like to go through some basics of images. So the color of every pixel can be determined by its 8-bit RGB value. RGB stands for red, green, and blue, and the three sets of numbers in this array respectively represent the amount of red, green, and blue that are mixed to form the specific color. With 8 bits, the maximum number of values in R, G, or B is 256. But because the number starts from 0, the max number is actually 255. As you may have guessed by now, an RGB value of 0, 0, and 0 will be black because it's supposed to represent nothing, while an RGB value of 255, 255, and 255 will be white. This is because white is actually an amalgamation of all the colors. The challenge of this script came when I had to decide how to compare the differences between two screenshots. In this example, we used two screenshots of 3 pixels big that are taken on the same light and same position during the lecture. As you can see, obviously, the two screenshots are exactly the same in the RG and B values, in exactly the same positions, namely the first, second, and third pixel positions. So let's say we take the difference of the first, second, and third pixels respectively between the first screenshot and the second screenshot. As you can see right here, the differences are basically all 0, 0, and 0. And what this means is that if you were to take a screenshot of this difference, it would just be a blank black picture. Now that we know how differences between images work, we can use 3 Python methods to compare differences. The first is a bounding box method. The second is comparing norms between screenshots. And the third is my most favorite solution that I settled on, which is the percentage black method. In the bounding box method, if all of the pixel differences are RGB equals to 0, 0, and 0, then the bounding box will return a non-object. In the first line of code as seen in the bottom example, the image chop.difference bracket IM and I'm next is to find out the difference in the pixels between two screenshots IM and I'm next taken at 2 different time points. So the second line of code tries to get the bounding box, and the code after that checks whether the bounding box is none. If it's an exact comparison, then the bounding box will be none. Since screenshots are taken at the exact same position and offset, theoretically speaking, the screenshots that are taken on the same PowerPoint slide should return a difference of bounding box none. However, when I tested this code, it still keeps giving me an object, showing that there is a very minor difference between the two screenshots. So let's go back to our examples again. Let's say we have taken the difference between two screenshots that are gonna ask a bounding box 1. The screenshots are 3 times 3 pixels in area. Thus, the difference between these two screenshots are also 3 times 3 pixels in area. The differences in the first to second and third pixels are all RGB 0. However, as you can see, the 5th and the 9th pixel has a difference. Thus, if you were to find the bounding box of this difference, it would basically return me a screenshot showing this area. As you can see that the RGB values are actually very low, almost near 0. Thus, the bounding box screenshot will actually show up almost totally black. So the bounding box is the smallest area encompassed by non-zero pixels, aka non-black pixels. In this other example of bounding box 2, bounding box 2 is returned from the difference between two screenshots of size 3 times 3 pixels. As you can see, there is now a difference of 0 to 0 in the third pixel position. So the bounding box difference will be of 2 times 3 pixels big. So when I tried out the bounding box method, it was horrible because it would still keep giving me screenshots of the same PowerPoint slide in the lecture. One possible explanation for this is the pixel shift. With our naked eye, the zoom window doesn't appear to move. However, at a pixel level, the zoom window may move by a few pixels up, down, left or right constantly to ensure it doesn't burn into the screen pixels permanently over long periods of use. You can think of pixel burning as some sort of scar that is left on the screen permanently. This is why when screenshots are taken at the exact same position, the pixels may still be slightly different. So after the first method didn't work, I went on to try the second method, which is using norms to quantify difference between images. So there's 2 norms we could use, either the Manhattan norm or the Euclidean norm. Let us refer to the example on the right. After we've taken the difference between two screenshots, we will get a collection of RGB arrays that show the difference between two images, and as you can see in the previous example, most of these pixels will be close to 0. So what we're going to do is to compress this collection of arrays by summing them up all together. Let's just assume that summing up all of these arrays will give you the RGB array of 6, 6, and 0. To calculate the Manhattan norm of this 6, 6, 0, we will just simply add 6, 6, and 0 together to get a distance of 12 from the theoretical point of origin, which is 0, 0, and 0. If we were to use the Euclidean norm, then we'll have to use the Pythagoras theorem, where basically we would take the sum of 6 squared and 6 squared and then add them together and then square root the whole thing to find out the Euclidean distance from the origin. Since the point of origin of 0, 0, 0 represents no differences between the two images, we can safely say that the greater the Manhattan distance or the Euclidean distance away from the origin, there will be a greater difference between the two screenshots. So this is how you do it in Python. Diff is a collection of RGB arrays that show the difference between the two images. Manhattan norm is just the sum of the absolute values of all of the RGB arrays. The Euclidean norm will be found using this Python function. What you get will be representative of the difference between the two images. Although this method enabled me to quantify difference between two images, regardless of whatever threshold I set, this method will still inconsistently take screenshots of the same slide in the lecture. In other words, norms between two different images was only slightly higher than the norms between two identical screenshots. And since there was no reliable threshold that I could set for every single lecture, I abandoned this method. This is the third and final method that worked so well. First, you analyze all pixels of the difference. Then, you calculate the number of pixels in that difference that are black. You do this by giving a black threshold value. So let's say if you want all pixels that have a sum of less than 50 to be considered as black in color. Python will do that for you, and then after that, you tell Python to calculate the proportion of pixels that are black in color. This method works so well because when I was playing around and trying to print out the difference between two screenshots as another screenshot, I noticed that the difference showed as almost entirely black for screenshots that were taken on the same slide. Meanwhile, the difference of screenshots that were taken on different slides would show up not entirely black and it will be noticeably brighter. Of course, I went to test out this method in real life lectures, and lo and behold, this method actually works reliably in all lectures, even when I kept the black threshold constant at 50. So when you open the script, what you need to do is to set the correct settings. So you just leave the black threshold as 50, the percentage black threshold as 98% should be good enough in my testing case. And you just need to change the screenshot sizes, X and Y size, and then the X and Y offset. You just leave the pause time as 2 seconds, which means that it will take screenshots every 2 seconds, and the rest of the settings you can just ignore it. Now while the script works fine and dandy, I went to add a hotkey mode so that I could take screenshots manually whenever I want. This works really well for lecture slides that do not show all of their content at once on a single slide. For example, they may add some animations that show the bullet points one by one. The problem with this is that it will be hard for my script to pick up a difference and take a new screenshot, but with the hotkey mode, I can decide when I want to take a screenshot. So here is where the hotkey settings are. To enable hotkey mode, you just change the hotkey mode from false to true, and then you set the hotkey that you want to use the screenshot with. So in this case, I set it to Ctrl+L, but you can set it to any other key that you want. When using this script, you must change the reference picture that helps this script decide where to take the screenshot from, together with the screenshot size and offsets. To change the reference picture, simply go to the project folders and then open the pics folder, and then change all of these icons to an icon that is seen in the top left of your windows. So in the zoom window, you want to take the top left corner of the zoom icon. The save icon represents the top left corner of your notes taking application, while the MS Teams icon represents the top left corner of the MS Teams application. All these pictures have to be unique and not be seen on another part of your screen. If not, the script will mistake it and take a screenshot from another reference point than you expected. So this script will still manage to paste the screenshot into your note-taking app, even when you're not on the note-taking app window. This is because it will locate the note-taking app icon on your screen and then move your cursor to it. It will click once so that it will bring up the note-taking app window, and then it will go to the next line and paste the screenshot for you. So the reason why I put this code here is because after we have moved the cursor to the icon which is at the top left corner of your note-taking app, we want to bring the cursor instantly back to its old position so that we can continue to use the cursor properly even while the script is running. Well, that's all for a coding project today. I'm going to share this project on my GitHub so everyone can use it. I hope you found this video enjoyable and also find a use for my script, because it has definitely helped me in not taking screenshots anymore. And I hope to see you in the next video.